This lecture will be about anomaly detection. The lecturer will be Stefano. So I already presented him 2 days ago. Just wanted to do a warning. So be careful to his jokes and laugh, because otherwise he feels bad. Okay.
Okay. So today our final lesson will be on one of the most fascinating and probably frustrating fields of machine learning, that is the anomaly detection. Usually when we talk about anomaly detection, it comes often this famous sentence from Donald Rumsfeld that talks about there are known knowns, known unknowns, and unknown unknowns. Naively, people think that everything with anomaly detection is strictly connected with unknown unknowns. But this is not completely true. Probably it's what we are mostly interested to, but it's not given that we're going to get. Another famous sentence that is often referred to anomaly detection is that searching for anomalies is like going in a dark room without a light, searching for a black cat that may be not there. But actually, I have to say that it's plenty of cat all around. The problem is that we may be interested in some different cat with respect to what we get. So basically, the expectation every time someone starts to study any algorithm of anomaly detection is that if I start from a dataset with 1 million of cats, I have to press a magical button, execute an algorithm, and then I can find the mythological cat never seen before, maybe mentioned in a weird cat dynamics theory. And then all that I have to do is write the paper and book my plane for Stockholm. Unfortunately, this is not the way in which it works. It takes a lot of work to perform this task, and often the answers are, well, complicated at least. In reality, we have to deal with, we will find something that is not our mythological cat. I'm referring here to images because it's easier to be visualized. But of course, this applies to tabular data as well. One kind of known unknowns that we have to deal with is the fact that some of the anomalies are just artifacts. So something that is visualized or produced in a table in a wrong way. So for instance, blurred images, defects of the pipeline that reduces the original data that you are using, and so on and so forth. Clearly, spotting even a large bunch of these will not bring you to Stockholm, I have to say. But if you want to look at the bright side, you can learn how to better filter your data set. So you can come out with a better filter. So it will also be something good, even if it's not what you are aiming to. Besides that, you can come out finding something that is not supposed to be there. Whenever you take a catalog, no matter how good is the catalog itself, there is no such thing as a 100% pure catalog. Any algorithm that performs a classification comes with some errors. And if the catalog is large enough, otherwise you should not apply any anomaly detection method. If you have just 3 objects, you can look at them and say, this is fine, this is not fine, and it's over. So you will come out often finding something that just should not be there. So it's a known known that you are not interested to. Again, the bright side is that if you are able to improve the classification that led to the catalog, you are still performing something interesting. But again, there is no room for Stockholm here. Another thing that you can find is something that is rare but not so rare. there are family of objects that are rare, that are studied. You can come out finding something of a rare family that has never been seen so far. That is interesting. And even if it's not your field of study, maybe you're not interested in study Sphinx, I don't know who actually study them, but you can create a better catalog, an improved catalog, and allow the community that actually is interested in Sphinx to study them. So still, it's interesting. And finally, what happens mostly is that at a certain point you end with something that looks perfectly normal. So at this stage, you are stuck. Maybe it's really an anomaly. Maybe it's really interesting. Maybe it's even worth to go to Stockholm, actually, but you have to study it. The algorithm is not saying it can give you some hints of why it's an anomaly, but could not say to you, this is this kind of anomaly, and this is the reason you need to study me. Basically, you have to spend a lot of time with follow-up, studying it, trying to understand why it's an anomaly. It's just something connected. Maybe in the case of the photo of the cat, can be just, it's something weird in the background, or it's something of a secondary effect. So it's a rare way in which the texture of the fur is, it can be a lot of things, but you need to study. So the algorithm is just saying, hey, look at this. But after that, there is all your work. And this the majority of the work. So just recapping those few words, there are no such thing as a import magic button predict on something. And the last time I did this presentation, after saying that half of the audience just step away and go outside, and no blame for them, and the remaining just PhD students that were actually writing their thesis and not listening at all. But, press the wrong button. But if I apply such kind of algorithm, for instance, to galaxy in the SDSS, it's just select all the galaxies with high quality data. I get basically everything I mentioned, except the ticket for Stockholm, of course. There are low quality data that were not supposed to be there, despite the flags. There are objects that were supposed, there are large objects. I selected something that was supposed to fit the thumbnail. And again, it was not supposed to be there. There are some rare objects, not so rare, and I was not interested to. And there are also objects that to me seems completely normal. So I get all the possible problem, but the ticket to Stockholm. Again, it's just an example, but is often what you will get. I'm sorry, but one of the problem is that the definition of outlier itself, it's tricky. Is the red cross an outlier? Well, the answer is depends. Maybe, but maybe, is just something that is a tail of the distribution. So you have just low statistics, but it appears as an anomaly because you don't have enough points for spotting it. So as I mentioned before, the size of the catalog plays a role. And how a classifier will answer to that? Most of the classifiers that you've seen in the last day will attribute this point to one class or the other, probably with a probability of 51, 52 with respect to the other one. So you can think that we can look at points with this problem, and then you can see that this is hard to be spotted because practically all the classifier will be completely sure that the point will belong to the blue class. And this is also why it's important to spot outliers even when you are not interested to them, because this will spoil the results of classifier and clustering methods, because this point unless of the law statistics and so on, should not belong to the blue class. So if you are studying the blue class, you should throw away the blue point, no matter what it is, because it's polluting your dataset. This is also known as overconfidence problem of classifiers, because it will be really sure about that. Again, it's quite complicated to say what is an anomalous point. The point with the red cross is an anomaly, or it's a point perfectly in the middle of a cluster. Well, again, it depends, because maybe if I add one more dimension, it's a huge outlier. So the answer could be adding as many information as possible. And no, it's complicated. I'm sorry. We mentioned it shortly. Simone mentioned it during the first day. It was also asked from someone with some more details. But even though adding information can improve your results, it's not given for granted that adding more and more information will bring something to your result. Usually, one typical example is that if you are interested in classifying bottles of wine and you have a list of features, the year of production not only is not helpful to distinguish between one bottle and the other, but can be even harmful, because if your sample of wine is biased in any way, because maybe you start buying Bordeaux starting from a given year just because of the way in which you are sampling your dataset, the algorithm maybe can fit around this feature. And this could be harmful for any algorithm, classification, regression, clustering, wherever. Because the algorithm tries to squeeze any bit of information from something that is not related with your target. This is something that Simone already shown, that the classifier that adding some features start degrading its quantities. This is known as curse of dimensionality, and unfortunately has nothing to do with pirates and wizards. But if you want to see that using cat and dogs, because of course it's the bad choice, I'm considering something really naive, so using the 3 channels as information, not something really pleasant. So if I start with just one feature, I could not distinguish between them. With 2, I start seeing some clusters of cat and dogs, but with 3, I maybe can be able to separate them. But again, this is not the final goal. I can go back to the 2-dimensional plane and identify the portion of the parameter space where they are separated. But the reason for that is I tried to explain that during Wednesday, when it was asked. Usually we consider as well sampled. This is an approximation. It's like to say that a cow is a sphere. It's just to grasp the concept. We can consider as well sampled the inner portion of your dataset, considering a square parameter space, the circle inscribed in the square, just because in the corners you have a lower density by definition, because here you could not have points on top. So they will be different from the others. Point in the corners will be perceived as different by definition. And for a geometrical reason, if I start with a circle inscribed in a square, and I move to a sphere inscribed in a cube, and then I go further with an hypersphere inscribed in an hypercube. This is an artistic visualization of a 80-dimension cube. What happens is that points goes to corners. Why? How does work the distance? It's just adding the square of the difference in a given dimension. So what happens when I add the dimension? There can happen two things. The distances can increase or stay stable. They cannot become closer when I add a dimension. And in particular, the only case in which no distance is increasing is when a feature is identically equal to one single value. And clearly, this is not a useful feature. A feature that is always one, it's not so helpful. So in all the other cases, geometrically, points are pushing away one from the others. There is nothing else that they can do. And in the end, when I consider the ratio between the hypersphere and the hypercube, so the significant part of the parameter space, this is going to zero. This ratio is going to zero really fast. And therefore, after a certain amount of dimension, every point will become a point of the corner, and that it's more probable, more prone to be an outlier. But after some bad news, let's look at a couple of strategies. They are not the only one, but they are the most popular one. The first one is the unsupervised anomaly detection. So basically, I take all the points that I have, and I present them to an algorithm. This algorithm will search for points that are abnormal with respect to the other that I have there. So the main pro of this approach is that I'm just using all the points that I have. I don't have to do much more than that. The con is that if I have enough anomalies, they start becoming normal. Because if the dataset is large enough and something is not just a single anomaly, clusters of anomalies are becoming similar. They could become similar. So I'm reducing the possibility to get something that is not unique. And if I have a dataset large enough, as I hope to, because it's better to have a larger dataset, I'm neglecting the possibility to retrieve this kind of cluster. The other possibility is working the other way around. So I filter my dataset. I take only the good points. I'm really sure about good points. And then I train the algorithm to say, this is normal. Wherever it's different from something here is anomalous. Then I can apply the new points and see if on any output they are different with respect to the other one. This is prone to two main problems. The first one is the purity myth is just a myth. Whenever you have a dataset large enough to make sense to use an algorithm like this, you will probably have something that is wrong in your data, despite the fact that you are convinced that they are clean. This is quite true. On the other hand, you have to be really, really sure that the new points belong to the same distribution of the points that you trained. Because if you perform a filter to select the points that are good, and you cut away systematically something, then wherever you put, when you put back the points that are being cut, it's something that is not being presented to the network just because you cut it away. This is one fact. The other fact that can come into play is that maybe if you train it on data that you get at a certain point and you present to the model something more recent, the instrument can be changed because, I mean, instrument tends to going slightly worse in time, then suddenly maybe you change some portion of the instrument itself, and suddenly the quality increases. All these changes, changing also how the points are being acquired. And for an algorithm in which you are trying to find something that is subtly different, this can be a problem, of course. And on the other side, you can also change the algorithm. So if you are improving the algorithm that redact your data, this can lead to a change too. So this second strategy is more prone to this effect. The other one is more prone to filter out wherever is in the data itself. And despite the strategy that can be, not all the algorithm can work on all of them, but most of them can. I'll present you in a few moments 5 different algorithms. I choose them for 2 main reasons. The first one is that they share some portion of the algorithm that you already met in those few days, so it will be easier to introduce them. And besides that, they use some concepts that are quite interesting, and they are different one from the other. So the first one will consider the distance. How far is this point? If it's far enough, could be an anomaly. The second one will consider the density. So this point is in a really, really low density region, and therefore it's isolated in a different way. The third one will use the concept of isolation. How easy it is to isolate this point from the others, like in an horror movie. Then I can try to reconstruct. I'm able to reconstruct this point knowing the other ones. And finally, just something that is connected with the geometry. So can I bound the class with a sort of membrane, and wherever it's outside, it's an outlier. So let's start with the first one. Oh, sorry. I have one final bad news for you. Most of the algorithm does not provide an actual flag. Several of them, when they say that this is an outlier, they are lying. They are just using a weirdness score that is cut at a certain point. And often when they give you a flag, it's just because one of the parameters is saying where to cut. Basically, when you have a weirdness score, there will be always a point that is weirder than the other one, just by definition, because this will happen unless the weirdness is equal for all the points. That is usually not the case. And where to cut is a problem. You can do several things. A lot of people work with the quantiles, for instance. I take the last 5 quantiles, for instance, and I take them away, or you can work with the standard deviation. So I take the average of this weirdness score and cut away at 5 standard deviation from that. It can be done. There are also people that just say, since I have to study the points that I select as an outlier, another reasonable strategy is to say, I can study 100 of them. So I take the top 100 and I study them. This probably will lead to with some referee can be tricky, but you can manage to do that on the other way around. I have someone that says that was using 4.5 standard deviation, and magically this was exactly 100. So I was not convinced that they chose this exact number for the purpose of statistics, but was mostly because they were able to study 100 of them in a reasonable time. But no matter that, this is something that you have to take in account. The first model, it's a slightly modified version of our friend, the KNN. In this case, I just take the neighbor and the radius, the distance for the cased neighbor, for instance, here is the third neighbors to our point. How this could help us? Well, I can build here a distribution of the distance. So each point, how far is from its cased neighbor. Therefore, if I have this bunch of points and the star is the anomaly, the distribution using, in this case, the first neighbor, not considering the points itself, of course. is that. And as you can see, the point that is isolated is well spotted really easily. So we can just use k equal to 1 and all of our problems are solved, except whatever, because if just I have a couple of points, like 2 stars there, they will be well hidden within the distribution of distances. Of course, if I change the number of the k nearest neighbor, this will solve the problem. So the solution is having a larger k, and of course, when I reach a large enough k, wherever will fall within the distribution again. And unfortunately, how many times I said unfortunately today? I'm sorry, but it's unfortunately. Yeah, we have seen metrics for classification, metrics for regression, metrics for clustering, but here it's hard to have a metric. The only way in which you can have a metric is to know some of the anomalies that you are looking for, and then you maybe try to optimize hyperparameters on that. But if it's a true anomaly, how you have enough of them to calculate something? Probably you have a couple of them, maybe 10. It's statistically relevant that you are capable to retrieve 5 out of 10 of them. Clearly, the other possibility, and it's often done, is to work with simulations. And again, on one hand, you have to truly trust your simulation, but if you have nothing but that, you can do so. But again, if you are interested in the mythological cat that no one has seen before, you probably have a really poor simulation of it. So can you trust it to search for that? Probably not. So the search for hyperparameters here, well, it's a mess at its best. But somehow it has to be done, so you need to hang tight whatever you have. So if you have a couple of anomalies that you already know, it's worth to look what happens to them. It's not statistically robust as we would like to, probably, but we do what we can do. When life gives you lemon, the only thing that you can do is lemonade. So, in this case, I presented to my friend KNN 2 clusters. I know that there are 2 clusters because they are produced actually using two Gaussianly distributed clouds. And then I added one red point that is an outlier. This was added on purpose by me. But if I look to the black point and I consider the KNN distance, the red point is way closer to the blue cluster with respect to one standard point of a sparse cluster. So in this case, the KNN would be, not probably, will for sure prefer to mark as an anomaly the black point with respect to the red one. And this could be a problem. So there is an algorithm that works exactly trying to minimize this effect. It's a version of the KNN because it shares a common part, slightly improved, improved, it's a strong word, because we will see. But it's a different version in which it calculates together at the first stage, the distance from the cased neighbor, and then to each calculates the distance of each of the neighbors selected at the first stage from their neighbors in order to see if the points it's isolated by itself or it's just in a sparse cloud. So basically, just to look it operatively, it starts. If I selected the third neighbor, So I get its radius that is 2.06. Then I take the radii of the third neighbor of each of the three neighbors that I've selected. I average them, and then I perform a ratio. If the ratio is way more than 1, with way more, it's something that it's completely on you, and it depends strongly also on the number of dimensions. If it's way more 1, this could be an anomaly because it's in a less dense region of the parameter space with respect to their own neighbors. This will work in any region of the parameter space. So if a point is close to a dense cluster, this will be spotted too. So for instance, the red point will have a 5 dot something loft value with respect to the sparse one that will be an inlier because it's less dense. The point is that so KNN and local outlier fraction will disagree on a lot of points, but to determine which is the right one, it's on you, because maybe this could be a local outlier or can be a good one, because it depends. If the red point is an extreme version of the green cluster, or it's an outlier of the blue cluster, the two algorithms will answer in different ways, and the correct answer depends on your problem. So there are no, I'm sorry, I'm really sorry, but there is nothing that works for everything. Otherwise, I will teach you just one model and say, use this and it will work. It will work. Another possibility is to use a modified version of random forest. With random forest, if you remember, we perform cut in order to optimize to the purity of the sample, which is fine. But here, we don't have a concept of purity. So the main idea is to perform random cuts on random features. That could not sound so good in that way, but the concept is just like that. If I cut randomly on one feature, and then a second one, this point has been selected randomly after 2 random cuts. This means nothing. But if I have enough trees, what happens is that points that are isolated will have usually a path length, the number of cuts that I need to isolate them, that is way smaller with respect to points that belongs to the inner portion of the cluster. Just because in order to isolate them, you need really precise cut. And since they are extracted randomly, they will happen rarely. Even if just by any chance, I can probably isolate this point with 4 cuts. If I search exactly the 4 boundaries, and this is hard to be obtained randomly, but even if this happens once, this will not happen for the majority of trees. So for the majority of trees, this will be separated with a lot of cuts, while the point that is in the top right corner will easily be separated with maybe even 1 cut, you can see. That's the idea of this algorithm. The third one instead is a modified version of support vector machines. If you remember, the concept of support vector machine was to identify an hyperplane that is able to separate linearly 2 classes. As we said, this has been implemented in order to work with the high nonlinear space using the kernel trick, but still you need 2 classes. The idea of one class SVM is to create a virtual enemy. So in this case, there will be a class that will be artificially added to the origin of the parameter space. And beside the standard algorithm, they will force also the boundary to be the maximum. You remember the idea there was to maximize the margin of the two classes. In this case, it's trying actually to push it as far as possible from the virtual enemy. There are versions in which you can also add to this virtual enemy some true anomalies if you want to push the results toward this selection. There are some works in literature in which this has been done, adding those more classes, and it actually worked. The point is that it's really important, the selection of kernel, and RBF is one of the best. If you remember, one of the examples that I did on Wednesday, where in the corner with RBF we started to see something appearing that we don't know what it is. It's because in the way in which the kernel is created, it actually tries to wrap something. So you will often have something actually wrapping your data. Another method that we can apply is an autoencoder. Giuseppe mentioned shortly them. It's basically a specific kind of neural network that has an architecture like that. The idea is that I'm not trying to targeting a class. I'm not trying to targeting a single value. I'm trying to targeting the input itself. So if I have, for instance, an image, I want to obtain the same image in output. The idea is that I start from the input data. I have some layers of MLP. Then I come to the bottleneck, that is the so-called latent space. And this first part is called often encoder because it's pushing the data from a higher dimensional space to a smaller one. So it's encoding the information. And then I have a second part that is trying to do the opposite. So it's decoding the information. And ideally, you can obtain the same input that you have in the first place. If this happens, then the bottleneck, the latent space, is a good representation of your data, because we are saying that all the points can be reproduced starting from that, because I can not use the initial layer. I'm using just the decoder. So start from the latent space and go to the reconstruction. This has been used extensively also for to generate new data, has been used also to generate simulation and so on. It was quite familiar a few years ago. There was an application on web that makes people smile. So the concept there was just an encoder in which the developers identify one of the dimensions of the latent space that is actually correlating with people smiling. So if I start with the original image, and my original image in the latent space has some coordinates, if I'm adding something to this specific coordinate, the reconstruction is just the original image, more or less, plus a smile. The concept is exactly that. But despite how the autoencoder works, the idea here is quite simple. If something is really rare or even not present in my training data, this network will not be capable to reconstruct the point from which I start. So if I have a good autoencoder that is capable to reconstruct most of the objects in my dataset and is failing on some of them, they could be at least points for which has not been trained properly, or it may be not even seen it once. So they could be anomalies. So for instance, if I have a sinusoidal data, it's quite complex to use autoencoder in 2 dimensions, so the visualization is often bounded to reconstruction of sinusoids, because it's the idea is pushing the number of dimensions to a lower one, and lower than 2 it's just 1. That is quite annoying for visualization purposes, but still the idea is that the reconstruction will be more or less good for most of the point, and then I suddenly have a huge error, and this could be an anomaly. I want to show you, like we did for the classification task, how those models will see the world, because the way in which they are constructed change the ways in which they see the world. So rather than show you that model by model, I decided to make a slideshow, let's say. So considering always the same point, if I use the KNN with k equal to 1, what I will see is basically just stone in the waters, because starting from each point, this point would be the center of normality, and wherever, as long as you go far from the other point, this will lead to an anomaly. Clearly, as we see, the fact that the anomaly is in the training data is changing strongly the shape of the world. When I move to 2, this effect is minimized, and moving to larger value is going to create something smoother and smoother. For the loft, the result is something that seems broken here, but is again partially due to the fact that I have one anomaly in the dataset that is changing the shape, and so it's defining itself at the center of a normality score. So wherever falls there, it's normal, because this point has a huge distance to the other one, and is pushing all the points to be less dense, and this becomes more and more normal after a while. And it's, in the end, it's not so different from the KNN in a general case, but it can be really different on specific case. So in a single point, it can be really different, but the overall context will be mostly the same. They share a lot of the concept. The concept, even if it's moved from distance to the density, is it's quite similar. Isolation forest with 1 tree, it's really dumb, and the only thing that they can do is performing rectangles, basically, because it's cutting on one dimension and the other, and all it can do is that. But when I move to a more reasonable number of 3, what I see is something like that. Still, I have the effect of the cuts that is quite evident. And even if we add more and more dimension, this effect will be minimized from a point of view of a human being, is still something that is connected in how the model is built. But it's not a big problem by itself, but it's something that we should know, that points will be selected according to something like that. For the SVM, we really depend on the two hyperparameters that we use. One is how I want to push, penalize the errors, like we did for classification. So how many points, let's say, are forgiven if are outside from the membrane, and the other one, it's the gamma, the exponential one from RBF. So in this case, in which I'm giving those two parameters, they looks like two big sphere, two big circle surrounding the cluster and the anomaly, but I can be more, I can go more narrow around the points with the membrane, or obtaining something really, really different in all the cases by changing hyperparameters. And as I said, we have here a huge problem in setting the hyperparameter. Without encoder, here I put just a PCA, because a PCA is actually an autoencoder with moving from 2 to 1 dimension. It's just to see something reasonable. This effect is mostly due to the fact that this algorithm should not be used with the low number of dimensions. But I want to show something to you, so it's here. And since I was scared to forget to mention that it's stupid to use an autoencoder on 2 dimension, I even wrote it down. So this is mostly what we have seen. The complexity is how complex is to be computed, but the results can be really different. One possibility more is to use more than one method, since they are selecting anomalies in different ways. And with more than one method, I also include with more than one configuration of hyperparameter. In this slide, I put just the 5 models that we mentioned. You can consider boxes with different configuration of the same method, and so on and so forth. And then you can, according to what you are trying to do, select, for instance, the objects that are anomalous for all the methods. So there should be really strong anomalies. Or you can select a majority class, so when the majority are selecting them, or even if you are searching from something that you think that is really rare and you want absolutely to have it in your final catalog, and you are willing to explore a lot of them, you can also consider the possibility to use an OR. So if any of the algorithm is saying that is an anomaly, then I take it. This is completely on you, but it's a possibility, and of course, using more configuration and more models is something that is helping with the problem that we don't have a proper score for those models. So my main conclusion here is that there is no universal way to identify outliers, also because there is not an universal way to define outliers. And there is not such thing like a model that is good for all the problems. And I say that at the beginning that is frustrating. So if you have any possible question, please. Or if you are not too depressed, at least. Io sono stato troppo veloce. Abbiamo il coffee break? Ok. Sì, sì.
Hello. Yeah, this is not actually a question. I would like to add something to the explanation. Thank you for the explanation. It's very helpful, even on my field. I would like to go back to the wine for an example, and I would like to add something from an archival point of view. You said that, for instance, in the wine dataset, the year was not important, was actually detrimental in terms of...
Clearly, it's just an example.
Yeah, but from an archival point of view, I would like to remind to all of you that when you acquire data, when you do a data survey, every kind of information is important. Maybe not to you, but for another scientist doing a different kind of research, the year of production may be helpful. Let's say they are studying how to relate anomalies in wine with use of fertilizers or something like that. Maybe the year of production for them may be useful.
Oh, of course, also the evolution of the wine across years.
Exactly.
It was mainly an example.
Yeah. But what I want to remind you all, even if you one dimension in your data set it may not be useful and you're not going to use it in terms of studying, please report it. Even if the dimension was constant, as you said earlier, was not useful in terms of the study, maybe added in the metadata of the data set, because it may be useful to characterize the data sets later. And for from an archival point of view, it's actually very, very useful. So that's just an addendum.
No, I mean, it's clear that the fact that the year is there as a reason. As I said, not all the features are useful for all the tasks. This is as general as possible. The radii that is present in an astronomical catalog is probably not useful if you want to study stars. The way in which they are derived can be optimized on a subclass of object also. So there are cases in which there are parameters that are meaningful just for some objects because they are designed to be derived for some object. But since the algorithm maybe often is dumb, it calculates for everything. Also because the concept of purity. So if I calculate it for everything, if I discover that at a certain point that something that I flagged as class A is actually class B, I already have it. Otherwise, it's lost forever. Again, the point is that you need to choose wisely your information according to your task. It was the idea when we had the feature importance and so on. Clearly, on this task, it's more complicated due to the fact that I don't have an actual metric that I can use on that. And this is the most disappointing thing, that I have two methods. One is spotting 10 outliers, the other one 8. It's fine. The only metric is study 18 of them and then say, well, the 10 were actually garbage, while the 8 are exactly what I were looking for. It's really frustrating.
Yeah, it's an addendum to the depression. It's just, science is not easy.
No, it's never easy, but there are tasks that are more, well, if you are trying to classify something, you will end with a classification score that can be high or low, but you end with the result. Here you can end with several, I don't know. And this is, yeah, getting not the best result is not an happy moment for anyone, but it still is a result. Here you can come and see why this cut is flagged as anomaly. Yeah.
Thank you for this lesson. And I understood that the majority of the responsibility is on the data set. So do you assume that the data set are perfectly classifying and perfectly regular, and among that data set you can find anomalies, or you can also find anomalies among irregular data sets? And which could be a correct way to do this?
I have to say that at least in astronomy, we don't have such thing as a regular data set. We don't have even such thing as a honest data set. Unfortunately, we have what we have, and we could not go there to check if the measurement is correct. So we have, in some cases, also, in particular, for the cases in which it's probably worth to explore if there is an anomaly, there are huge error bars on everything. And also the signal to noise ratio for the images is generally lower because, I mean, I do not expect to find an anomaly that is worth to be studied in the local universe, for which we have wonderful images, well-studied objects, and so on and so forth. We often want to do that on points that are really faint, or with observation that has a cadence that is not perfect, and so on and so forth. So, as I said, we have lemons, so we need to deal with that.
Okay. Just a question about autoencoders. You show that when the dimensions are low, they usually generate with a sinusoid.
No, I'm reconstructing a sinusoid just because it's easy to be visualized with an autoencoder. The autoencoder, if you have, it's not reconstructing a sinusoid, no matter what the data are.
No, because I was thinking if the expression in the latent space is poorer, then it will reconstruct with something that is easier, like a sinusoid, or
No, I'm just saying, if I have to plot something with few points using 2 dimension and an autoencoder, the simplest thing that somehow works is an sinusoid. Okay, but it's something related to the data that I used, not to the method. But again, it's a method that should not be used with such a small number of dimensions. But just because the idea is that it's good if it's capable to encode data, the information. If you have no information to comprise, is okay. Okay, so if you have no other depressing questions, I can start setting the notebook, and then someone stop me when we have to go to the coffee break. Okay. I hope that you can see. I zoomed it enough. Oh. Okay. Often in this notebook, most of the code is required for visualization purpose. It's actually quite simple because all the models works practically in the same way that we already seen. So here, well, the first cell is clearly the all the import that is possible, some configuration about the graphical instruments and so on. So here the first idea is to initialize and see how some models work. So again, the instances are the same that we had for all the models. So we have the model and the hyperparameter, and you have to declare them. Basically here I'm just fitting recursively all the methods on the points. Clearly, the only one that has a difference is the autoencoder, because with respect to the other one, has a target. Even if the target is the input itself, it's different with respect to the other one. Then I'm creating a bidimensional grid for which I will have the prediction in order to visualize in the different region of the two-dimensional space if the algorithm will select them as an outlier or not. So I have, and here for some of the models for which the reconstruction, the output is in the other way around, I multiply it by minus, but it's just visualization. So if I run this because I didn't run the import, this can be helpful actually. Without the import, it does not work. So this is, I'm using a sinusoid here with the three. Probably I need to unzoom it slightly. Okay, with the three outlier injected in. So most of the points are regular point on a sinusoid. I have a point that is really easy to be spotted. One point that should be quite easy, and this point can be problematic because it's quite close to points that are good, and we can see how different models react to that. So the idea is exactly what we saw. This is since this is far from the other with k equal to 20, this is becoming this is spotted basically, while those 2 points are trickier. For the local outlier fraction, this is clearly, as we expect, an outlier, while this one is completely not. It's completely within the region where the density is reasonable, and this is somehow halfway. Again, different models will spot it differently. Here you can see also the effects of the cuts from the isolation forest. And again, this is clearly an outlier. This is an outlier for most of them. For one class, this is failing because they I explicitly say to the SVM that this is a good point. So this is how tricky is to deal with the wrong outliers in the dataset. And again, those 2 points belong to the surface. This depends clearly on also on the upper parameter, and we will see better that this is with the PCA, and this is an actual autoencoder that is doing something quite stupid because it's not supposed to work that way. Going more deeply, we can see how the multi-density problem is treated differently from a KNN and a local outlier fraction that is capable to disentangle that this point is far from the neighbors in terms of density, while the KNN is saying that this is way more weirder than this. This is a difference by definition. It's the construction of the method that will lead to different answer in 2 different scenarios. And here, this is. Here I can also see what happens by changing the number of neighbors dynamically. So if I choose this effect, we have the masking effect in which the neighbor is the center of normality, and clearly it makes practically no sense. But when moving with different, a larger value, this is where the three outliers will fall, or the global outlier is still far away. If I select a lower number of points, I can retrieve all of them, and clearly, if I go to something really large, the two outliers that are close enough to the original or to the actual point are completely in it. But still, it's interesting that the global outlier is still spotted by the method. So I need to go really, really far in terms of number of neighbors that I'm selecting. After that, the global outlier falls within the distribution. So despite the simplicity of the model, is still capable to perform the task, at least on strong outliers. That is something that is not given from grant, even because we just saw how the one class SVM that is way more complex is not capable to distinguish when the point is in the training dataset. We can work in the same way on isolation forest, where one of the parameters is the contamination, and the contamination is exactly the way in which the isolation forest is tricking you. You are saying that you want 1%, 5%, 15%, whatever percent of contamination, and then it will cut for you the outliers, but it's just depending on this parameter, basically. So it's the output is a flag, but it's a fake flag based on something that you decide. So it's probably worth to use directly the score, the weirdness score that is built in. Otherwise, you come with a cut performed by someone else based on a number that you put randomly or most. Clearly, if you want to use percentile, it's basically the same thing, so it can be done, but it's not a good idea. If you have, of course, if you have some kind of information about the points, you can come out with something that is similar to a confusion metric. So I can say that those are true positive, true negative, false positive, and false negative, but you need to know the truth for some of them. If you are in this condition, you can come out with metrics that are similar to the one for classification, but it's quite hard to have something like that for anomalies, I'm afraid. With the isolation forest, the contamination, as I said, plays a role. And here you can see that the boundaries of the output is always the same, exactly as I said. But the point flag, I need to, otherwise it's not seen. The anomalies are the ones surrounded by the circle. So the boundaries are exactly the same. The only difference is what is selected by this cut. So it's a parameter that is quite useless from this task. It's more helpful to change the hyperparameter, the shape of the trees, with respect to change that. Okay, so let's go to the coffee break with 2 minutes in advance. It's I mean, the point here is better to change the way in which you build your trees, so how depth they are, how many they are, rather than change a value that is just performing a cut that you can do by yourself, by cutting somewhere here. It's exactly what it's doing. Nothing more, nothing less. Okay. Here in this further cell, I'm trying to use one of the hyperparameter of the random forest in order to avoid the effect due to the presence of mini clusters of outlier in your training set, that, as we saw, can be harmful for the model, and this can be done using the so-called masking, in which basically we are saying that each single tree should be trained on a subset of the data. Here I'm saying the max sample, and therefore we will see how using or not using this parameter will change. Will change the results. In this case, where I'm not using the max sample, and I'm using basically all the subset that is the default value for isolation forest, this micro cluster of points is still classified as normal, while the only anomaly that is identified by the model is this one. In this other way, the effect of this microcluster is somehow suppressed, and the algorithm is capable to spot them as a microcluster of anomalies. Again, if this is a good effect or a bad effect, the fact that you are missing or not missing this cluster as anomalies depends on your task. Because I could not know in principle if those are actually anomalies or it's a cluster of very well-known things. So again, this parameter has to be assessed by its own. For what concerns the SVM, here we have also a recap of the hyperparameter, and this is the result. And here we can play with both the hyperparameter. Nu is the one that penalizes that allows the two anomalies to be just out of the boundary. So if I move that, this will result in changing slightly the shape of the membrane and is enlarging or reducing the number of anomalies flagged by the model. While gamma is instead the value of the radial basis function, the exponential part, and this will change a lot the shape rather than the height of the membrane. So it can result in very different way in which here is more capable to identify local zones of the two moons dataset, and I can bring it up to something that maybe you don't want. Please note again that this point is in this case is flagged as an anomaly with respect to the to some example before. I can do that also with an autoencoder. Here the structure is to have 16 neurons, then 8, 1, and then going back to 8 and 16. It's a very, very simple autoencoder, probably the dumbest thing that you can do in this field, but I was not interested in using a more complex structure like you learned with Giuseppe on Wednesday. But all the tricks that he talked to you can be applied. For instance, the dropout. Clearly, in this case, it makes not practically any sense, but it can be applied. So. In this case, the autoencoder is capable practically to spot only the one with the highest error. But again, it's a model that is supposed to work with more complex data. Clearly, you can look at the learning curve, since here you have something. In this case, it's trained on something. It's trained on the reconstruction of the input data. So you have an actual training phase and you have a target. So with respect to the other method, you can optimize the autoencoder also for anomaly detection. Because you want just to reconstruct better, but obtaining a perfect autoencoder that is overfitting is not good at all. So in this case, it's probably worth to have a validation and a test set as we performed in supervised learning, because this algorithm, we are using it for anomaly, but is actually working supervised in order to reconstruct the input, the original input. We mentioned the curse of dimensionality. I just decided to see what happens if I had some noise dimension that are pure random uniform noise, and then it's scaled, and the result is that okay. Basically, we can see how the F1 score on the known anomalies. Please consider that they are only 3. It's not so effective. It drops dramatically for some of the models, while the isolation forest is still capable to keep some consistency after a while. Also, the area under the rock curve can be done for the 3 anomalies. In this case, I have that I already know. Again, it's something that it worth to be looked at if you have some anomalies for which you know the truth, but statistically, it's something that you could not defend. That makes no sense, a rock curve with just 3 points. But since it's all that you have, it's worth to at least to a look. Here I built also a consensus model, and here you can see how for which point all the various models agree. For instance, this is really simple, and all the models are agree on that. At the same time, this is an anomaly for 4 models, but we need to notice that also those points that are on the edge of the sinusoidal shape are spotted in the very same way. Once we have one anomaly, what I can do is try to understand if some variable is actually working really to set it as an anomaly. This is not so useful for 2-dimension, of course, but once I have a lot of dimension, this can be done. One possibility is to replace the value of a single feature with the average of all the feature of all the values in the dataset of this feature, and see if the result is changing. So I can see how much it's changing by replacing one feature. This can suggest to you if one feature is leading the detection of the anomalies. Clearly, it's slightly more complicated when dealing with images, sorry, but can be done on tabular data, something like that. It's quite simple. Moving to a data set that is the same that we used for the exercise on Wednesday, the breast cancer. I considered just 5 points from the malignant tumor as anomalies. And the first thing that I suggest to you to do when searching for anomalies is to look at the distribution of features. As you can see, a lot of the anomalies are already in the tails of the distribution of practically all the features, although it's not given that all the things that are on the tails are anomalies. It's worth to be to take a look at that. I can also try to perform a 3-dimensional PCA in order to see where the points are. We can see that some of them are quite easy to be identified through even through a simple PCA with 3 dimensions, but still it's something that is this point is clearly with respect to the other data an anomaly, but it's not what are we looking for. So again, the problem is moved from what is statistically an anomaly and what is an anomaly that is of any interest for you. That can be really different. I can perform, of course, the same exercise in order to to see where the anomalies are, so I can change the contamination of the isolation forest here and just see where in a 2-dimensional PCA plot they fall. And also in this case, even with the few anomalies for which I know there were 10, not 5, but it's the same, I can obtain different results. And clearly this depends on your task. Again, it's the same about the nuclear plant. In some cases, you don't want to lose any possible explosion event with this, even at the price of shutting down the nuclear plant, sometimes that is not needed. again, depends on your task and how many of them you want to analyze. In this case, for instance, at the price of analyzing 41 events, you will take all the known anomalies. So there is a huge chance that if there are other anomalies, they fall within these 31. But again, depends on your task. And this is the same trick that I did with 2-dimension, just considering the 5 most scoring reason to be an anomaly for this method. This is a quick recap. And here I have your exercise. So you have about an hour to do that. I take the wine sample and I adulterated some of them, actually adding the values that we know that make the wine become a poison. So it's really important that you spot all of them, because otherwise some people will die. So here you have your data. Data preparation is here. And then you should just, and you have also the, let's say, the schema of what you have supposed to do. So train the model, try to evaluate on the marginal knowledge that you have. If you are able to spot all the bottles, please try to keep all the people alive. And maybe try to perform some visualization and the explainability. So understand why those bottles are being flagged as anomalies.